Hi viewers, I am creating these videos to help teachers of maths support their learners in making sense of mathematical concepts and their associated procedures and processes. And today what I want to look at is the long version of the column multiplication algorithm. And I've got my place value counters out here ready to help me make sense of that. I could use Dean's here instead, but and particularly if learners don't have a good understanding of place value and how 10 ones is equivalent to a 10 and 10 tens equivalent to 100, then I might have to use Dean's to help with that so they can see 10 ones becoming a 10. But of course, you can make the argument that if they don't have that understanding of place value, then they probably shouldn't be doing this anyway. So the place value counters is just going to be a little bit tidier than having all the blocks all over the place. It's going to be a little bit tidier, a little bit neater for me to show this. So let's have a look at a multiplication. I want to look at the multiplication 32 times 27. Now we know from the long multiplication algorithm that in effect here, I'm going to do two different multiplications. I'm going to do 7 times 32 and I'm going to do 20 times 32. So in order to do this multiplication, what I'm really going to have to do is I'm going to have to do this twice. I'm going to have to set up a 32 to be multiplied by 20, and I'm going to have to set up a 32 to be multiplied by 7. And I might choose to set both up before I start, or I might choose to just set one up and do the multiply by 7 bit and then do the multiply by 20 bit, but I'm going to need these both at some point. So the way the long version of the column multiplication algorithm works is kind of like the short version in that it uses broadly a repeated addition style model for the multiplication. So here I've got my 2 ones, and I'm going to multiply those by 7 by repeating them 7 times. So now I've got 2 lots of 2 ones, and then 3 lots of 2 ones, 4 lots, 5 lots, 6 lots, 7 lots. So now I have my 7 times 2, and we can see that there, 2 repeated 7 times, and that's given me a total of 14. Now, of course, in the algorithm, I can't write 14 in here because I can only write a single digit in each place. So what I'm going to do now is I'm going to group some of these ones together. There we are. And so now I've grouped those into a 10. Now I'm going to keep that 10 out of the way for a minute because I don't want it involved in my next multiplication. But what we can see here is that what I've got now is I've still got my 14. Seem to have inherited an extra 1. I've still got my 14, but now I can see I've got it as 4 ones, and then I've got an extra 10, which is not going to be involved in my multiplication, but I do need to consider it at the end. And now I'm going to do the same thing with my 10s. I'm going to multiply this whole block of 3 10s by 7. So I'm going to see 7 repeats of that. So here is 30 times 2, 30 times 3, 30 times 4, times 5, times 6, times 7. And so again, I can see I've got way more than 10 10s here. So what I'm going to do is I'm going to start grouping those together. And those are going to group into a single 100. And then I've still got more than 10 10s here, so I'm going to group some more together. And those have grouped into my next 100. And I've still got this 110 left over. So here is my, in effect, 7 times 30 being 210. And then I've got my extra 10 from before, So all together there, I have 220 plus my 4 ones. So that's the result of multiplying my 7 by 32, is to have 220. And now I've got to go and multiply my 32 by 20. Well, of course, to do this, what we would normally do in the long division algorithm, the long multiplication algorithm, is just stick a 0 here. And if you think about why we're sticking the 0 there, it's basically because we're saying to multiply by this 32 by 20, I'm first going to multiply it by 10, which is going to increase its place by 1, and then I'm going to multiply the result by 2. And actually, again, this is the sort of thing we're going to have to model using these counters. So although I've set up a 32 here, what I'm going to say is, right, I'm going to multiply this 32 by 10. And if pupils, again, if they're secure enough in their place value, they might know that that means this 10 is going to become 100. And I might just be able to swap this 10 out for 100 straight away, and similarly. Or what I could do here is say, right, I'm going to multiply this by 10. So that's by 5, 6, 7, 8, 9, 10. And then, of course, because I've multiplied it by 10, each of these is now a column of 10, which I can group together. And then similarly, I'm going to keep that to one side for a minute. Similarly, each of these, and some of those ones are still hidden under there, but I can put these together and group those together. So my 2 1s now in effect have been replaced by 2 10s. And then I can do the same thing here with my 10s. I can multiply my 30 by 10. So there's 2, 3, 4, 5, 6, 7, 8, 9, 10. And then I can start grouping these together. So I can group some 10s here. Thought it might do that. And then I've still got clearly lots more 10s, so I can start grouping some of those together. 2, 3, 4, 5, 6, 7, 8, 9, 10. And then finally, I can group these 10s together. And so we can see, in effect here, what I've done is replaced my 3 10s and 2 1s for 300s and 2 10s. Now, as I'm sure you'll appreciate, that was quite a long process, particularly given nothing had to be written down for that, save now writing a 0 here. So it's much better there if pupils are happy that when I've got my original 3 10s and 2 1s, that because I'm going to multiply each of them by 10, I'm just going to swap a 10 for 100, 10 for 100, 10 for 100, 1 for a 10, 1 for a 10. Okay, rather than having to actually show the repeated addition there. But now that I've done that bit, I can now say, right, well, now that I've multiplied it by 10, which has the effect of putting the 0 here, I can now multiply everything by 2 because I've already moved it up the correct place. So now I can multiply my 20, what is now 20 by 2, and I can multiply what is now my 300 by 2, which is again just repeating. And so what I can see now is I've got 600s and 4 10s, so 640. And then, of course, having completed these 2 separate multiplications, the algorithm then suggests that we should be adding these together because I've got the result of 32 times 7 here, the result of 32 times 20 here. So if I add those together, I'll have the result of 32 times 27. And of course, for adding them there, it just means I'm going to collect together my bit. So actually, technically, according to the addition algorithm, I should collect my ones first. I have 4 ones. Of course, in this case, it doesn't matter because there's not going to be an exchange going on, but occasionally it will matter. So it's worth sort of sticking with the established algorithm. I'm going to add my ones. You can see I've only got 4 ones. I'm going to add my tens. So I had 2 tens and then I add another 4 tens. So there's my 6 tens. And then I'm going to add my hundreds. I had 2 hundreds. I'm going to add another 6 hundreds to it. And the result is I have 8 hundreds. So that's broadly speaking sort of the sort of mechanics behind the column multiplication algorithm, the long version, and how that sort of works in terms of how we model that multiplication. Broadly speaking, it's a repeated addition, but there's a little bit of sort of tweaks in there. There's sort of a repeated addition with the 7, then there's a second one, but as part of that repeated addition, because I'm multiplying it by 20, there's a recognition, potentially at least a recognition, that in multiplying it by 20, I can multiply it by 10, which will shift everything up a column. And so all my ones become tens, all my tens become hundreds, etc. And then rather than multiply 32 by 20, I am in effect multiplying 320 by 2. And that's what produces the second line. And I can keep going and put some hundreds in here and what have you, and start bringing in thousands, or even change so I've got my 10,000s or 100,000s if I need to. But to be honest, if the point where we're trying to multiply things that are going to result in 10,000s and 100,000s, if we're still relying on the place value counters to allow people to make sense of what's going on, then we probably need to take it back to some simpler calculations before, so that they can get used to sort of how that's working and not need the manipulative in order to deal with larger calculations. So that's my short video on how the sort of long multiplication algorithm works, the long column multiplication algorithm works with regard to manipulatives. What I'd like to say, as always, is a big thank you to Mathspot.com and its creator Jonathan Hall for providing such a wonderful website for which I'm using to create these videos. And if you've never been to Mathspot.com, please do take the chance to have a look. There is a huge amount of stuff on there, not just the virtual manipulatives, but lots and lots of stuff to help teachers of maths with teaching their pupils. And if you are interested in manipulatives and using manipulatives and visuals to help make sense of mathematical concepts and their associated procedures and processes, then you might want to check out my website, visiblemaths.co.uk. And amongst the many things you'll find there, you may well find a link to a copy of my book, Visible Maths, and the publisher's website for that, which is Crown House Publishing. On their website, they have a selection of sample pages that you can view. And of course, if you feel like it would be useful, you can place an order. I will be making these videos throughout lockdown and potentially beyond. So if there is a particular concept or process or procedure that you feel like you'd like to see worked with manipulatives and how manipulatives can be used to support making sense of it, then please do get in touch and hopefully I'll be able to provide one for you. Thank you very much for your kind attention.